Okay, well, all right. Welcome everyone to today's seminar. We had a cancellation, so I thought I'll tell you about my work because I think my first talk was more an overview of the institute, and I didn't get to talk about some of the aspects that I work on. And this talk was put together in a short time, so it's a little bit of old work, but I think it will help make connections. That's my hope with people both within the institute. Especially highlighting the human aspect of things, how that interfaces with AI decision making, and hopefully beyond the institute as well. Always look for new collaborations. Okay, so with that, let me get started. I guess we are seeing more and more use of AI, or at least attempts at incorporating it into autonomous decision making. So you're all probably familiar with, I don't need to even go over these, but autonomous navigation is a clear example of that. Another one you have probably encountered are recommendation systems. So anytime you click on Netflix, Google, buying a product, right, or any of these product-based systems, there are algorithms behind the scenes working to recommend products to you. That's also autonomous decisions to what product should be shown to you, depending on your past history of clicks, what movies you have watched, what products you have bought, and so on. Another one that I've worked on a little bit myself is material science experiments, or broadly scientific experimentation. So even there, we can use AI algorithms to decide what are the next sequence of experiments to run based on past observations. And this is particularly useful when your state space is very large, what you're searching over, right? So you're trying to design the material. There are so many configurations that are possible. If we can use, autonomous algorithms, then it can help search through that space efficiently. Now, the machine learning methods that sort of fall or that address this autonomous decision-making aspects fall under a spectrum of algorithms here that are broadly categorized into, let's say, active learning, optimization, bandits, online learning, reinforcement learning, and many other variations. I'm going to focus on one of them called bandits in particular, though I'll mention some extensions that we have to, like reinforcement learning and other scenarios briefly. So let me set up the bandit framework for decision-making, autonomous decision-making. We talk about it particularly in the stochastic context, which will become clear as I talk through it. So let's think of any of the applications I just talked about. In these problems, there are certain actions we need to choose from. So of course, where to turn, for example, in an autonomous navigation system, what specific configuration of atoms to try out in a material science setting, and of course, what product to recommend, right? So these are the actions or the decisions the algorithm will be making. And in a bandit setup, we believe that it's a sequential decision-making setting. So there are different rounds characterized by time step here, T going from 1 to T, where you get to take an action or make a decision. We also refer to it as pulling an arm. Somehow bandit literature got fascinated with like, you can think of it as like sort of what is it called? Like a slot machine kind of setting where you pull arms and get rewards. And that's why it's often referred to as an arm. You pull that arm, meaning you take a corresponding action, and you obtain a reward that's stochastic. So there's a mean reward function, and then there's some noise added to it. And what you observe are these noisy rewards anytime you choose to do an action. And of course, you do this in rounds. So you repeatedly are trying to pull different arms, take different actions, and figure out which one yields the maximum reward. Right? In the case of a recommender system, you're trying to figure out which product will give you the most click-through rate, for example. Now, there are many goals here that you can aim for with bandit optimization. I'll bring out some of them that are most popular. One is to minimize or find the best arm, essentially, right? So that's just, A star is your action that gets you the maximum reward, and the goal is to find that action, right? Another way to measure the reward or the goal that you have is to say that you want to make sure not only that you pick the best arm, but you actually want to just ensure that the reward of whichever arm you pick is close to the reward of the best arm. That's called simple regret. And we can also talk about cumulative regret, which means that as you're taking these sequence of actions, the goal is not just to find the best arm or try to get close to its reward, but you actually want to ensure that throughout the different steps, your reward that of the actions that you're taking stays close to the maximum reward, at least as much as possible. So you measure it in a cumulative sense over all the decisions that you have made so far. Okay, so this is, again, recommender systems is a good example of that. You don't just want to find the product that the customer will buy, and you want to keep recommending and hope that in between they're clicking on things that still give you some reward, right? Not just the maximal reward. So the key difference between these settings is that the first two sort of belong to what we call explore-only setting, which means you can just keep exploring different actions or options in this case, and then come up with an estimate of which one is the best, whether in terms of exactly identifying it or in terms of getting closed in regret. But in the cumulative regret setting, you also need to do some exploitation. So there's an explore-exploit trade-off that comes in, which is you're trying to find the action that gets you the most reward, but in doing so, you also have to make sure that you're not just randomly exploring. You want to be able to explore good options such that the reward you accumulate as you're exploring is not too bad. So you also want to be exploiting the promising actions while you're trying to find the best action. Okay. Now, there are two key challenges that sort of come up in this framework that I'd like to focus on today. One is, where do these rewards come from? Right? They are actually very hard to obtain. Very often, we just come up with mathematical constructs that make sense, that may not actually capture what the human decision maker may have in mind. And we often see AI algorithms actually running into this problem called reward hacking. They often hack the reward metric you give them. And you can clearly see an example here, right? If you just say that I'm going to give a reward, if the agent starting from the initial position reaches the final position, it might take a shortcut that you may not have planned, right? And there are numerous examples of, you can just search the words reward hacking that come up for autonomous algorithms doing that.
Humans are also really good at reward hacking.
Humans are also very good. That is true. Yes. Yeah. In this case, what we have in mind is that we're not able to fully capture in the mathematical reward notion what the human may have had in mind, or when we were trying to solve a problem. Yes, but you're absolutely right. So we hope here that the question we ask is, can it incorporate human feedback, right? So we can't just ask them and come up with the appropriate metric that will capture their goals, but can we obtain feedback from that throughout the process in the form of indirect rewards? So these could be comparisons between actions, right, that a human can provide, thumbs up or thumbs down to different, recommendations made by the algorithm, and we may be able to use that to, in addition to the reward that we may have come up with, to help improve performance. So I'll talk about this setting a little bit. And the second hard challenge I talk about is that rewards are often dynamic. And so they are harder to learn, which means that the rewards keep changing based on the actions that you have taken in the past. An example of that is, and that aligns with some of the stuff that I'll talk about, is if the same product is shown to you or similar products are shown to you over and over again, you may lose interest in it, right? Or maybe if you do it multiple times, it might actually increase your engagement with that, like depending on what thing is. So polarization, for example, happens very often. If you start following certain line and you keep reading material on the same topic, you can get polarized in that direction. So either way, right, rewards can certainly change, and that's why dynamic rewards are hard to learn. And of course, this is addressed by the standard reinforcement learning kind of setting, but reinforcement learning, unfortunately, tends to be very expensive in terms of the requirement on how much data it needs. So we'll bring in some effects here coming from, again, thinking about the humans in the loop, right? When the rewards are coming from human, then we see that oftentimes the reward might actually depend only on the number of times an action has been taken in the recent past. I'll explain this more as we go, but essentially we'll be trying to bring in some memory effect that, yes, there is dependence on past actions, but that dependence might only come in terms of how many times a particular action was taken. Or we'll call it the calibration effect, and I'll explain it a little bit more as we go. But I just wanted to highlight that these are two aspects I'm trying to cover today. So for the first one, let me say a little bit more. We'll look at incorporating preference feedback from humans. Okay, that's the first theme I'll talk about. And so here you can look at, again, feedback in the form of trajectories in autonomous navigation, a thumbs up or thumbs down, comparing two trajectories, right? So human can look at two movements of a robot and say this trajectory is better than that, right? Another place you may have popularly heard of it now is large language models like GPT and so on, were trained using human feedback on similarly, trajectories of sequence prediction of text. Another is preference for products, just thumbs up, thumbs down, whether you like a product or not. And even in this scientific domain example that I talked about earlier, we can actually obtain expert feedback in the form of which configuration is more likely to yield to the desired property or not. And we can actually get such feedback from experts because the experiments are often expensive to do, where you can actually measure the true reward, but you can ask an expert about their judgment. And in fact, in some preliminary work we did, we were able to show that a data and expert hybrid system can actually do better than just leveraging data only. Okay. The second part that I'll talk about, which is about incorporating memory and calibration effects, essentially goes with the idea that, so this comes up a lot of time in particular like psychophysiology literature, that I think this plot is from one of those papers. It shows that as you keep doing a task, you might get better at it, right? So your error kind of goes down. That's what this plot here is showing. I mean, imagine any game you're playing, basketball, darts, whatever, right? Your performance tends to improve. Similarly, if you're trying to do a complex task, the more you do it, you require sustained exposure because before you start achieving your performance on it, like what your best shot may be. Similar things happen in, as I mentioned earlier, in when you are indicating preferences for products, right? You may be, the more you read about, one side of the, well, whether it's political view or, whatever other view, you may tend to align with it more and more. Okay. So these are just motivations. And I wanted to make sure that everybody gets that piece of motivation. And then I'll go deeper into these two topics. If there are any questions, please feel free to ask anytime.
So in the first topic, the role of the human is to provide feedback.
Yes.
Like all bandits that learn stuff, like they get some feedback. It's
Yes.
just in this particular case, it's a human providing the feedback rather than the environment.
Exactly. Yeah.
Okay.
Yeah. Yeah. So the first one, humans will be providing feedback. The second one, we are just modeling some effects that humans may have because they tend, their performance tends to take some time to settle down, let's say. All right, so let's talk about the first one, which is incorporating preference feedback. And I'll talk about it in the context of bandits. So we'll look at bandit problem. A standard bandit problem will only have pulse, which means you choose an arm and you observe the noisy reward. Right, and in addition to that, now we also consider a dueling setting. So humans are better at doing comparison as opposed to providing a reward. If I talk to my material science collaborators, right, it's very hard for them to say what the property of a particular material configuration may be, but they can say this one is more promising than this, right? And this comes up in many, many scenarios. So human feedback often tends to be in the form of comparisons. And so we look at the setting where we have access to both some expensive pulls, but also some duels, where now what you get is that you pick a pair of arms and you get to observe a comparison, whether the reward for one is larger than the reward for another or not. And of course, you get to know this in a noisy fashion. So it's noisy feedback, right? So yeah, this happens in, again, we can do it in scientific experiments. We can do it in under any kind of peer review setting, assessing the difficulty of reading passages. That was one of the data sets we worked with. Admissions, hiring also, right? You can compare two candidates easily, but then to actually like get a sense of their qualification, you may have to invite them for an interview.
Aarti, can you hear me?
Sorry, go ahead.
Yes, I have a question. I'm wondering what is the relationship between the human preference and the objective value of the option. So
Yep.
I'm assuming that there is an optimal value, right? Assuming two alternatives, you know which one is better. The human might prefer the better option, but also the human might prefer the other one. I don't know how do you reconcile the preferences with the objective value?
Yeah, so I'll get to it in a minute. Basically, you're asking about what's the relation between the underlying reward that a person may have in mind when doing a comparison to the actual reward, right?
Yes.
Is that, yeah. I'll get to those assumptions, and people have made various types of assumptions there. In this specific work, I'll mention what we use in the specific work I'll highlight here, but we have also looked at where there may not be, like this assumption may be misspecified. So what the person has in mind may be quite different than what the actual reward might be. But I'll say exactly what the assumption we need for this particular piece of work. So just hold on for like a couple of more slides.
Aarti, there was another question in the chat here. And this was recent, so I think it references this slide. This is mainly when individual sample reward is not feasible to obtain, but pairwise feedback is.
So yes, we are considering settings, but I think the work extends beyond that. But let me say what, yes, we started doing this work in the setting where the pulls were, the direct reward was expensive and comparisons were cheaper. So we were thinking about how we can leverage comparisons in addition to the direct reward. That's the work I'll talk about. But in many settings, we have also just looked at what can you do if you're only given pairwise comparisons. Like, for example, in reinforcement learning, when you're only given comparisons between trajectories, what you can do. But for now, let's think about that. And you can also have, so you can extend this to say now there may be a cost to obtaining a direct reward and a dual or a comparison. And you can then talk about if you have those costs, how you can change the algorithms to adapt to that. All right, so let me just say a little bit about at least the specific work I want to talk about here, which is, let's just talk about what's possible with just comparative feedback here. Okay, so suppose you were only given comparisons between these arms, right? Then there's actually a bunch of work on what is known as dueling bandits. And essentially, you can show that duels only suffice for finding the best arm. If all you care about is finding the best arm, then you can just do comparisons and you can essentially sort your arms in the order from, right, the smallest reward to the largest reward, and that works. And it is true in general that if you're using comparisons for any kind of optimization task, right, finding the best arm is like, right, you're just trying to find the optimal value of that, right? And similarly for policy optimization and reinforcement learning, we actually show something similar is true, that using duals only, you can get the same sample complexity as you would get if you only had rewards. That's true in many other optimization-based settings.
It has to be like a blended setting. There's a consistent ordering, and you're just trying to sort of like find it over time. It cannot change over time, or
yeah. So yeah, this is in the banded setting, but in reinforcement learning also you can do that where it's over trajectories, right? And you can allow for noise and so on. Yeah, I'm just trying to give the high level sense here. Yeah. Okay, so for standard bandits, yeah, you could just use duals and that would suffice. You would never need any pulls. So we actually considered what is called the threshold bandit setting. So here the goal is that you actually want to find all arms that lie above a particular threshold. Okay. So with high probability, find all arms that are bigger than, let's say, a threshold tau. And of course, this can happen because you want to screen, right? So you want to say all materials that are like, or configurations that are promising. They give me my property larger than some value, or find all promising candidates, right? So you may be interested in a problem like that. And in this case, you can see that you actually require both duals and pulls. Just one of them is actually not enough because you need to be able to get a sense of the value, not just which arm is best, but which one is large. So this gets to, what is the link between the duals and the pulls we assume? The question that Cody asked. So first we define what is called the Borda score of an arm. That's just basically the probability that the given arm will beat a randomly chosen other arm. Okay, or the average number of times an arm beats any other arm. Okay, so we define these Borda scores for each arm, and these are different than the rewards, the mu's that you will obtain. These are based on comparisons, right? And now we can specify our assumption which links the two. So there are many assumptions that exist in literature, most popularly the Bradley-Terry-Luce model, but also Thurston model. There's strong stochastic transitivity, weak stochastic transitivity that people have considered. And just to give you a sense, they basically talk about if my rewards, true rewards, the mu's in this case, differ by a certain amount, what's the probability of making an error in comparison? That tells me how far the Borda scores are. So it relates how far the Borda scores are to how far the true rewards are under some manner. Maybe they're linearly proportional, or it's some other polynomial power, right? That characterizes the more parametric sort of assumptions. The particular assumption we use, go ahead, Bridget.
I'm just wondering how you can get threshold information from rank order.
You can't, that's why you also need the pulls.
Got it, okay.
Exactly,
Thank you.
Yeah, that's why we switched to the threshold bandits and not just regular bandits, but yeah. So the only assumption we actually need is that if an arm has, basically if two arms lie on opposite sides of the threshold, then their Borda scores will be in order, right? So Pi will be greater than Pj if one of the ith arm is larger than tau and the jth arm is smaller than tau.
Cody has another question.
Yeah.
She's asking, is there an assumption that human preferences are consistent?
So weakly in this particular sense, this is what this assumption says. So a lot of the other assumptions are stronger. They actually tell you that, okay, if the reward changes by this much, the probability that I will make a right judgment, right? The more the difference in the reward, the better the human will be at doing this comparison. And what we are assuming is something weaker than that, which is just that if you're on the same side, you have consistency. But in other work, which I decided not to show here because it's more complicated, you can also allow some misspecification between that your Borda scores may not exactly be matched with what your underlying reward function is. In this case, they are matched in this sense of this assumption. So just to highlight what this means, maybe I'll just clarify that a little bit. What it says is that my comparisons, right, remain consistent with whether my reward is above the threshold or not for arms that are on different sides. One of them has smaller reward, another has larger reward. My comparison will be correct, but my comparisons can switch for two arms that are both either below the threshold or above the threshold. For those, there has to be no consistency.
Sorry, I'm still
Yeah.
confused. The human who's giving the rank order information doesn't know what the threshold is. So I don't see how their accuracy can be improved by whether the two options are on opposite side of the threshold. Suppose we took all of the values, the mu's,
Yeah.
and we reduced them by a factor of 10. So now they're all below the threshold, but all the rank order information and all the ratio information is exactly the
Right.
same. Would not the human make the identical pairwise comparisons as they would have when some were above the threshold and some were below?
You're right, yes. So the human would, right? So this is just an assumption which is saying, yeah, that's a great question. And this is just saying that your preferences remain consistent if they are on the same side. But if they are all below or something, we're not saying anything about that.
What do you mean consistent
Right.
if they're all on the same side?
If they are on, so if one of them is
If
larger
they're
than the
on
threshold, they're on opposite sides. Sorry, that's what I meant. If they're on the same side, then you're not making any assumption about that.
Okay.
Because then it doesn't help to identify which
maybe
ones are
that's
above the
a
threshold.
To me, the threshold is irrelevant to the person who's making the rank
Yes,
order.
but that's why the comparisons are also irrelevant in that case when the arms are all below the
I
threshold.
get that the comparison is on you, that is, what I'm objecting to is the idea that the person will be more likely to do the wrong rank order if both options are on the same side of the threshold than if it crosses, because the human doesn't know that the threshold even exists.
That is true, yes, yeah. So that's why you could also analyze under stronger conditions, which actually relate this difference, right? Just the difference in the rewards to the difference in the probability. This is a weaker assumption than that. And yes, you're right that humans may not actually even follow it, right? Or it doesn't, it's too weak maybe, right? And if we actually wanted to model humans, maybe we should make some stronger assumptions like the VTL model. But those are a specific case. The algorithm will work more broadly, but yes, it can give you improved results if you actually make stronger assumptions. That's the way to interpret it. But you're right, if you were applying it in the human context, maybe you do deploy those stronger assumptions because you know the humans want to make those. Yeah, that's a fair point. Hope that helps. Okay, so yeah, I think I made this point already that this is weaker than the standard assumptions. So we can think about this first in the noiseless case, right? So in the noiseless case, just an analysis using only pulse shows that the number of pulse needed to find all arms with a threshold above more than tau looks like this. There are k arms, so it's the sum over k, and it essentially depends inversely proportional to the gap between the reward of that arm and the threshold tau, right? Which intuitively at least makes sense. And what you can show that if you use duals, then you can actually, especially if they are perfect, noiseless, then you can essentially rank your arms as we talked about, right? From increasing to decreasing order or vice versa, and then just do a binary bisection over that to identify which arms are above the threshold, which are below. And that's the only place you're using pulse, right? To do the binary bisection. So, and we all know that if you're doing binary bisection over k pieces, you can actually do it in log k attempts, right? So essentially you get in the noiseless case, you expect that, you will just sort your arms and you get this improvement in sample complexity, which is the number of pulls you will need would now only depend logarithmically on k. instead of linearly. And of course, you can ask, well, what happens in the noisy case? So of course, one idea is that you take your comparisons and you try to come up with this ranking. It will be a noisy ranking some way, and then I still run binary bisection over it. Turns out that is actually suboptimal because you incur too much error in the ranking. But if you did this repeatedly in epochs, then it makes sense. So that is basically what the noisy version of this algorithm looks like. We call it rank search. But you can essentially start with the set of active arms being the empty set. You rank, actually that should have been all of them, I think. While active arms is not the empty set. Yes, that's how I have to read it. So you start with all of them as your active set, and then you just use the fraction of wins, you use duals, right? With certain number of other arms, and we'll keep changing how many arms you dual against, depending on a parameter gamma. So gamma is, think of it as our confidence. Initially, it's large. We don't know which ones will beat the other ones. We start with some large value, and then we'll keep on changing that. And we just do binary search to find which arm lies closest to the boundary. Okay. And if we do that, then we deactivate all the arms which have fractions of wins more than this gamma factor, essentially, 2 gamma in this case, over k star plus 1 and less than 2 gamma over k star. Right? They're easily defeated by these boundary arms in duals. So we can deactivate all the other arms. And then we shrink this gamma. We are more confident now in the arms that we have. And we keep repeating this process. So it is still a rank and then do binary search operation, just that we are doing it in multiple rounds. We are throwing away arms as we go. And this actually gets you the best complexity here. So we can show, as we talked about, that if you have pulse only, that's the complexity. And even in the noisy case, you can get it to essentially log k, except that there is a slight extra factor, which depends on how hard is it, how much noise is there in the comparisons, how hard is it to for the pulse to give you the ranking, essentially. And the number of pulls, of course, also depend on this. You can show that the number of pulls also depend on how hard is it to distinguish these arms based on the noisy information. And of course, that intuitively, at least to give some sense, depends on this gap between the two arms that are, or the border scores of the two arms that are closest. Okay, and in fact, we have a lower bound that says that this complexity is almost optimal. So there are some actually extra factors, but I won't go into it here. If anybody wants to chat, I'm happy to chat offline. But we have a lower bound that basically says that any algorithm will identify all the arms correctly with high probability, as long as, the way I read the sentence is, as long as either the number of pulls is for that particular arms is bigger than the gap squared, or the number of duals is bigger than this border score gap that we talked about between the best arms. So if either you have enough pulls or enough duals, then you can identify this. And this pretty closely matches. I think there's a slight gap there that can potentially be improved, but it pretty closely matches the upper bound. So we applied this to some settings. Here, first, there's a synthetic setting, and there were no algorithms that looked at incorporating both direct pulls and comparisons. So what I'm showing you first is just a comparison in terms of how many pulls are needed with algorithms. The two, so rank search RS is our algorithm. That's the one at the bottom, requires the least number of pulls. And there are two different, I guess, distributions of the rewards that we consider. But the other algorithms are either simple label, which is you just obtain labels equally for all the arms, same number of labels given your budget, or you do them using this CLUCB algorithm, which was proposed for threshold bandits and more adaptively allocates the number of pulls depending on whether the arm is close to the threshold or not. And you can do better than both of those, mainly because you're leveraging comparisons. And then we can also compare the number of comparisons needed with algorithms, which essentially look like variations of rank then search. So they first rank all the arms using your noisy comparisons and then do binary bisection over them, but they just do it in a one-step manner. And there are two different algorithms that were proposed for that, but they did not do this in epochs. So you can see that actually they have much higher dual complexity than doing it in epoch steps. And in terms of real data, we applied it to a data set that was available on evaluating the difficulty of a passage. So it's a reading passage, which has difficulty levels 1 to 12, and we just set the threshold to 7. Can we identify all passages that are above that threshold or not, using comparisons? Now, there was partial comparison data in the data set that we obtained. So we first use it to train a comparison model, a parametric model for the comparison noise, and then we drew additional comparisons from that. And again, we have the comparisons with these existing algorithms that I talked about and can get improvements over both baselines. So that was just a sampling of work we have done on preference-based learning. I just talked about the threshold bandit problem because it was a little intuitive to think about, because you can like sort things and then use pulse on top of that. We have also looked at how can we leverage comparative feedback for classification problems, for different regression problems, both linear and non-parametric regression settings. And we have also looked at using comparisons for, as I said, reinforcement learning, where we looked at only comparisons, and we showed that the sample complexity you get, how many comparisons you need to do over trajectories, is comparable to the number of direct rewards you would need. Provided, of course, one comparison is providing information over an entire trajectory. So as long as you equate that with the equal number of direct rewards, you actually can do as well. And we also applied this to other non-convex optimization problems. And this is the work if you want to look at like mismatch between the function from which you might be getting the comparisons and where you're getting the direct rewards from. This work addresses some of that and how to adapt to that mismatch. But I just picked a simple one here to discuss so that it hopefully makes.
Can I ask another question?
Please go ahead.
Could you talk about why are comparisons like cheaper than a poll?
So they don't have to be. That's why I said we can incorporate costs if we know what cost is in a particular problem. In some cases, comparisons may
Why
be.
might it be? Because like this is sort of a mystery in cognitive psychology, right?
Okay.
It's true that humans are better at doing comparisons than
Yeah.
single evaluation, and yet it's bizarre because to do a comparison, you have to get the information about this option, get the information about this option, and then do a comparison.
Right.
Whereas a poll is just getting the information about this option. That's fewer cognitive actions. Why wouldn't that be cheaper?
It depends on the complexity of the task. And yes, there are tasks in which polls are cheaper and there are tasks in which comparisons are cheaper, right? Like if you have to actually look at very detailed information about each particular option before you can give a comparison, then yes, comparisons don't help as much. They don't reduce the cost. But in some of these papers, we actually looked at data sets and the reaction times of people in giving comparisons versus polls. And some of this data set, you can actually see that the comparisons are actually much cheaper than the reward.
I totally.
So for example,
I'm interested in the cognitive architecture that makes that so.
Okay, would love to hear more on that. And I'm not, that's why I wanted to mention this because I wanted to get feedback on like, what are natural, formats to consider here for when comparisons can really benefit. Well, at least one particular data set that comes to my mind was where I think you looked at asking people to estimate like the age of a person versus just saying which one is older or something like that, where there was this difference. But there are others that exist in literature.
Are there metric versions of this? I guess you could imagine a case where there's like a distance between all of the pairs or something, where we get like noisy distance values or something instead of just pairwise comparisons.
Sure. So you're saying, there
It's more
exists.
structure.
Yes.
It's like metric space rather than
Yes.
just like partially ordered separately.
Yeah. So what you're asking is essentially where you get differential information. Here, what you're getting is a sign of the difference. Exactly. Yeah. So I mean, there are like clearly optimization algorithms that do that, like gradient descent or something.
Yeah.
You can think about it and sign. This would be like equivalent of a sign gradient descent. So I think people have looked at some of that work as well. Yeah. I think we were just maybe more motivated by the human setting where dual seem to make more sense.
Aarti,
Yes.
I don't know if this is the right time for this question, but in decision sciences, there is an area of research that is called decisions from experience. And bandits are actually probably the most common way to study decisions from experience. So people are provided with two options, and each option is associated to a particular distribution of outcomes and, the probabilities and outcomes combination. And people basically explore those options by clicking into buttons and observing an outcome. So they develop preferences for some of those options over time. There are tons of very large data sets coming mostly from modeling competitions. And I'm wondering whether that would be something useful for this project, because essentially we have the dynamics of the preferences from humans over time, over a very large number of problems.
Yes, yeah, I think that would be really interesting to actually like learn these preferences, right? I mean, it seems like that data set would cater to it, right, on how people change or maybe develop. So maybe that even the next part that I'll talk about, like calibration effects, I think some maybe models for that, we'll just make an assumption that I'll mention. And the type of data sets you're talking about can actually help us learn what that correct model should look like, right? Based on observations of how people change their or settled on what preferences they develop.
That's right.
Yeah.
Because
capturing the dynamics of the, right.
Yeah,
Sorry,
in that area, there is no concept of this two-way comparison. I'm sure people are engaging in that comparison, but it's more about the learning of the preferences based on the feedback they receive from the outcomes of these alternatives.
But isn't it, I thought the setting was still that you're presented with two options and then the users click on one.
Yes, that is correct.
So that is like a comparison still, right?
Yeah, so I guess what I'm saying is mostly these settings don't have any explicit attributes. So basically they are just learning from the outcome feedback. And, people select because it's stochastic. You can have all sorts of outcomes in each option, right? And there is an objective expected value of each of the options, which of course participants don't know it. So they are learning over time what they prefer the most. Through these kind of very simple settings, there have been some interesting discovering. For example, when there is an outcome that is of very low probability, people tend to underweigh the probability of that event from experience, and therefore stop choosing that option that has that outcome. So anyway, this is sort of behavioral effects that I'm wondering how they would link to yours, but it's more about the dynamics rather than,
yes. Yeah, here we assume that the preferences are coming from like some underlying function, right? Like which could be linked to the true reward or not, but it's fixed. And actually the next part I'll talk about does look a little bit into the dynamic aspect of that. But we just assume models as opposed to,
Sorry.
it's okay. You have data which we can use to actually inform how people learn these preferences. Yeah, that would love to chat more on that. Yeah. It's very relevant. Okay, so yeah, let me quickly go over the next part. Actually, am I looking at the time correct? I think I may be already out of time. Is it?
We're at 3:45, so you're okay.
Oh, it says here 3:57. Okay, that must be wrong. Okay, I have a few minutes then. Yeah, the clock is wrong. Okay, so I'll try to quickly say a little bit about that. So here we looked at incorporating memory and calibration effects. And the idea is that, yes, a reward can change depending on the actions that are taken in the recent past. So that's where the memory bound comes in, that we only look at, certain number of steps back. So basically now your reward depends on the past sequence of M steps. And this is actually nothing new. The reinforcement learning setting exactly gets at this when there are dynamic rewards. So you take an action that changes the state of the environment. In this case, maybe the human, if they're providing the feedback, right? So the reward changes every time you take an action. The only problem is that if we treat it as, let's say there are K actions and we have a memory bound of M, then in general, if you treat it as a reinforcement learning problem, then the state space really explodes. There are k actions for each of the past m steps. You could have taken any k. So k to the m is the number of states you could be in. And that really blows up the number of samples you need in general, if you don't make any further assumptions on your reward. So we were interested in, this is highly inefficient. Can we actually do something that's polynomial in the memory bound? And so the kind of assumption we looked at is called tiling bandits. It's essentially based on this idea, again, that the more a product may be recommended to you, that's likely to change your opinion about it. So we characterize the reward as a function of only the number of times you took an action in the past n steps. Okay. And there is prior work under the tiling setting also, mostly looking at memory bound equal to the entire history. And people make different assumptions like monotonicity, convexity, and so on to talk about what happens there. And it turns out that if you actually don't restrict M to be finite, you go all the way back to the entire history, which is capital T, you do need some of these assumptions. So we tried to study this in the setup of, can we get sublinear in T and polynomial in this memory bound regret without any additional assumptions on what the reward function might look like. So in some settings, it might make sense that the more you show it, maybe the more polarized you're becoming. So it is an increasing or monotonic function, or that you lose interest and it becomes decreasing. But we wanted to do it without these assumptions to consider a general setting. So I'll talk about, again, how much time do I have? I'm thinking if I should skip this or not. 10 minutes or?
Yeah, you're good on
Okay.
time.
All right. So yeah, one way you can do this, especially if you have noiseless, so suppose there was no noise there, right? Then you can just do explore and exploit. You explore every option for m steps. You can just calculate what the reward is because it depends on those past m steps. And then you can offline plan the optimal policy for the remaining steps and do that. Turns out this explore and exploit actually achieves the optimal complete policy regret in the noiseless setting. But in the noisy setting, if you try to do this, you incur a much worse bound because you're essentially trying to estimate the reward of every possible action sequence of length m, whereas some of them may be suboptimal. You don't need to spend as much time learning about their rewards. So you can do something more adaptive and better. And so what we show is that, first we show that actually cyclic policies are a good solution, meaning that for every problem instance, there is a root T cyclic policy that's near optimal. And we can just do, I won't go into the algorithm here, just because it's more complicated, but you can successively eliminate, just like we successively eliminated arms, you can now successfully eliminate root T cyclic policies, and you can get actually a complete policy regret, which scales linearly in M and is sublinear in T, which is what you would like, without any additional assumptions. We're not making monotonicity or any such parametric assumptions on the reward. And in fact, there's a lower bound we show, which says that there exists a tiling bandit problem for which the complete policy regret of any algorithm is bounded below, which is essentially linear in M and root T in the horizon over which you're solving the problem. So it's almost optimal. But the algorithm actually computationally is very expensive because you are listing out all root T cyclic policies and then trying to do successive elimination over that. So we wanted to consider a more efficient algorithm, and we also wanted to consider a more general version of this. So instead of just tiling, we actually consider what's called a weighted tiling bandit, where now the reward depends not only on the number of times you take an action in the past, but with some weight. It's a weighted summation of the number of times action was taken in the recent past. Okay? So you can think of it as, you have an indicator vector which tells you whether that particular action was taken or not. You have a set of weights, unknown weights, and what you're observing, your reward is a function of that inner product of those two vectors. And first, we can show that if you make no further assumptions on your reward, this framework with the unknown weights is actually not solvable. I mean, it becomes exponential in M now, your regret. So this is not good. But that's when we went to this assumption coming from more, I guess, this was psychophysiology literature, which says that humans actually have what is called a calibration effect or repeated exposure optimality. The more we do something, the better we get at it, right? You can think of it as calibration, right? You're getting calibrated the more times you attempt something. And this is exactly what the assumption says. I'm not writing it mathematically. We're just saying that there exists an action such that if you play it repetitively at least m times in a row, then you incur better reward than any other action sequence, right? So if I keep reading polarizing blogs, which say yes to let's say a debate, then I will become polarized in that direction, and that will give better reward than any other sequence I may consider, where I read a polarizing blog, don't read an opposite blog, and so on. And similarly, like in any other games, dart throwing or basketball. So now, under this specific assumption, now we show that the problem of weighted tallying bandit actually becomes feasible. So successive elimination with just explore then exploit, where you are using explore then exploit, but you're doing it in rounds, changing the epoch size every time, actually achieves a complete policy regret that has very nice properties. It looks linear in M and root T in K, and also the algorithm is efficient. You don't need to do this over cyclic policies, you're just doing it over the original K arms, and it works really well. And there's a lower bound, which is says that this is a pretty much optimal. You can get. So just I'll quickly show some experiments on this setting as well. So we looked at both a synthetic setting, but also semi-synthetic setting, where we took the parameters of the setup from this paper that was coming from the psychophysiology literature. And you can see that SE, which is our successive elimination algorithm, tends to get the lowest regret in both setups, whereas other competing algorithms are UCB, which basically samples every arm. It's the upper confidence bound, for those of you who may not know that. Samples the upper confidence bound m times and then repeats that, or these other algorithms that target traditional regret or complete policy regret. So let me just get to conclude by talking about some open questions and directions. So first, one question that came up in this work was, well, does the algorithm need to know the memory bound, right, M? And it turns out that you can have an upper bound on M. And of course, you can run the algorithm with that. You can still get sublinear in root T rate, but you actually cannot adaptively get rates that depend on M. You do have to pay a price depending on whatever is the upper bound you assume on how far back in history you go. So we have a lower bound that says you can't do better for a given upper bound. You do have to incur a cost proportional to that. Without this restricted, the repeated exposure optimality, right, which is this calibration effect, the algorithm still is computationally inefficient. So efficiency is an open question there. Also, there was a slight gap between the bounds, regret bounds. And I guess what I'm most interested in is more natural models. So this is feedback from all of you, right, especially the social science folks, about what are other natural models of human performance beyond calibration that we can bring in, right? There are concepts like fatigue, right? If you do the same thing over and over again, not only do you get better, which is what you assume in calibration part, that's the initial part, but if you keep doing it, you might get fatigued, all right? So how can we model that? How can we model rebound effects? And there are many other natural human effects that we may want to model. So yeah, I'd be happy to discuss comments that you have about those. And just referencing some of this. So this is work that appeared in Cold last year and ICML. And there, this is the work of really, I think, Yichong and Dhruv, who were two students with me and some other collaborators. So happy to take more questions.